This is a video lesson for our final lesson of Unit 5, which is testing a claim about a proportion, which is really what we did throughout Lesson 2, Lesson 2, but this one will be like the whole process and not breaking it down piece by piece. Given that this is the last lesson of our unit, just a reminder, we'll be testing on Tuesday of next week. We'll have a couple of review days to get ready. So the how-to, this should look extremely familiar. This has been the same exact slide I've been putting up in every single lesson. Hypothesis tests are very consistent. There's just a few things that we change throughout each one, and that's really test statistic and occasionally how we find the p-value. But for the most part, the exact same 6 steps we've been doing all along. So here's our problem today. It's very similar to the problem that we did in Lesson 2, except for we have a lot more evidence in this problem. So the XORT is a method of gender selection that promises couples of having an increased chance of having a baby girl. Among 726 babies born to couples using the XORT method in an attempt to have a baby girl, 668 of the babies were girls and the others were boys. Use these results with a 0.05 significance level to test the claim that among babies born to couples using the XORT method, the proportion of girls is greater than the value of 0.5 expected with no treatment. Okay, so this is kind of a loaded question. First of all, we've got to find the claim. That's the most important word you're going to see. So claim that. This is going to tell us what our hypotheses are. Okay, that claim is always really, really important. Because we're talking about the proportion of girls, this is a proportion problem. That 0.5 means 50%. So right here is the biggest thing for our claim. This is suggesting that p equals 0.5 to be like the undisputed fact. Everybody believes that 0.5 is your chance of having a baby girl, and our test is going to show, or hopefully show, that the probability when you're using this selection method is actually going to be different than 0.5. So let's get started with our process. First step is to set our hypotheses. So we're going to be setting a null and an alternative hypothesis. Well, we're talking proportions, so it's going to be p for each of these. And as I said, the claim is talking about 0.5. So 0.5 is going to be the number aspect of these hypotheses. Automatically, your null hypothesis is always in equals. Always. So that half is done of our hypothesis. And now what we're really looking at is, all right, what are they talking about? Are they talking about less than, bigger than, not equal to? What are they saying? And they say the proportion of girls is greater than. So that is going to be a greater than symbol. And those are our hypotheses. The null hypothesis is that the proportion is 0.5. That's the status quo. That's what we expect. And the alternative is, you know what, actually it's bigger than 0.5, the chances of having a baby girl given this treatment. Easiest question we could get. Next, what's the significance level? Well, our significance level is stated to us here. They want us to use a 0.05 significance level. So we're going to say alpha equals 0.05. Now they want us to calculate the appropriate test statistic. This guy is our test statistic for this section. Okay, it can be very confusing because you've got p's and q's and p hats, and knowing which comes from the hypotheses, which comes from the evidence. Where do we get that q from? That can be confusing for some people. It is a z, which means normal CDF is coming up here, but let's kind of break this down. P hat is the sample proportion, so we're going to get that from the evidence. P is the true proportion, which we're suggesting to be 0.5 in the hypotheses. Q comes from P, so we're going to do 1 minus P, because Q is the true probability of not being successful. So if we're suggesting the true probability is 0.5, that would mean the true failure would also be 0.5. So let's start plugging in what we know. Z equals P hat. Well, let's go back to the evidence of this problem. In this problem, they say 668 out of 726. So our P hat is going to be that. We're actually going to have to calculate it. Our P hat is going to be 668. I'm going to write this off to the side. P hat equals 668 divided by 726. Which means for this problem, P hat is going to be, I'm going to go get my calculator, 0.92. So our evidence, which this is pretty staggering, 726 couples, so 726 births, 92% of them were girls. So we're really confident that we're going to end up rejecting here, but let's go through the evidence and do it. Okay, so 0.92 is our P hat. P from the hypothesis was suggested to be 0.5. Square root of PQ, again, that's that 0.5 for P from the hypothesis. Q is 1 minus P. Well, if I do 1 minus 0.5, I'm going to get another 0.5. And N is our sample size, which was that 726. Let's be really careful as we enter this into our calculator. My guess is we're going to get a real big number. So I'm typing this in. I'm putting parentheses around my numerator, divided by the square root, and that's going to be 0.5 times 0.5 divided by 726, and we get, that gives us back on our calculator 17.78, which is a very large z-score. That's 17 standard deviations, almost 18 standard deviations away from the mean. Okay, so I start to draw my picture here. I'm going to draw a normal distribution. And 17 standard deviations can be really far from the middle, but we'll just draw it right here. Okay, our alternative hypothesis was a greater than, which means we're going to shade to the right. So, in theory, we should be writing normal CDF, left bound, which would be 17, right bound, which we normally write 10, because 10's a pretty good approximation for infinity. So 10's basically infinity, and we're already at 17. We're way far away. We don't even need to do this to call it 0 plus, but if we really want to, we can. Let's just pick a ridiculous large numbers for z, 9999, which you'd be surprised to know that's not that much different than 10 when we're talking standard deviations, because 10 is already so far away. But we'll put a ridiculous number in there just to show it. 0 and 1, okay? And now let's go and see what our calculator gives us back for that. Normal CDF. Lower bound 17, upper bound 9999. I'm being dramatic by putting that. And my calculator says 4.35 e to the negative 65th. So that means they want 64 zeros before you write your first digit. Okay? That's why we're going to call this 0 plus. You're going to reject this at any level. It's a ridiculously low probability. Meaning that there's pretty much no chance that you're going to get 722 or 726 babies with 92% of them being girls if something weird isn't happening. So this is going to be a very easy rejection problem, and our probability, we're just going to call it 0 plus. Again, if you ever have a bound that's bigger than 10, like 17 was, where you can't even put 10 as your right bound, if you're ever that far to the right already, there's no need in even doing the problem. Just call it 0 plus, and you're going to reject pretty much automatically. Okay, so now we're in this technical conclusion spot where we're going to say p-value less than alpha. Well, our p-value is 0 plus, so it's definitely going to be less than whatever alpha was. which for this problem, I believe we set alpha to be 0.05. I'll double check. Yep, looks like we set it to be 0.05. Okay. And then we're going to just follow the script here. That's a rejection. Reject the null hypothesis because p-val was less than alpha. So state this conclusion. There is sufficient evidence to show at the 0.05 significance level that, and then alternative hypothesis in words here, the alternative hypothesis says X sort increases the probability of having a baby girl. When you're saying the probability is greater than 0.5, you're saying you're increasing the probability of having a baby girl. And that is our non-technical conclusion. That is stating it in a way that most people would be able to understand. Let's put this all together for one more problem. A recent study showed that 53% of college applications were submitted online. Assume that the result is based on a simple random sample of 1,000 college applications with 515 submitted online. Use a 0.01 significance level to test the claim that among all college applications, the percentage submitted online is equal to 50%. Okay, so let's focus on the claim, because the data here is a little weird that this is saying 53% and then we have 515. Well, I'm not even worried about this. I'm going to focus on what the claim is. The claim says it's equal to 50%. So let's start there. Okay, I intentionally gave you a little bit of a weird problem. Okay, so our null hypothesis is going to be based on that 0.5 from the claim. The proportion equals 0.5, which means the alternative hypothesis is going to be the proportion, and the claim is equal to, which means there's no direction suggested here, so we're just going to say not equal to 0.5 is the alternative. We've been told to use a significance level of 0.01, so I'm going to say alpha equals 0.01. And now we're ready to go get our test statistic. Our test statistic, as seen in a previous slide, is z equals p hat minus p over the square root of pq over n. Well, our evidence says 515 out of 1,000. I'm not sure where that 53% came from. That must be a typo or some kind of issue. Okay, we've got 515 over 1,000. That's the evidence we can actually deal with here. Okay, so our p hat, I'm just going to write it up here where I've got some space. Our p hat's going to be 515 out of 1,000, which is more like 51.5%. Again, I'm not sure where that 53% came from for this problem. Okay, so this is p hat equals 0.515. So we're going to put that into the problem. 0.515 minus, our hypothesis said that 0.5 was p, so p is 0.5, over the square root of pq, which would be 0.5 for p. This is another 50-50 problem, and whenever p is 50, q is also 50, so another 0.5 here. All divided by n, which was that 1,000 pieces of data. So we're going to put over 1,000. And now we're going to go find our z. On the calculator, that is going to say 0.515 minus 0.5 divided by the square root of 0.5 times 0.5 divided by 1,000. I'm getting a z-score of 0.949. I'm going to make a little bit more room for myself here. Okay. We next want to go and get our p-value. Okay, well, my p-value is going to require me drawing a picture of a normal curve. Z is over there in the middle at 0. 0.949 is bigger than 0, so we're going to put it somewhere over here, 0.949. Now, direction for this problem. We're going to go to the right because it's a not equal to and Z is positive. If it were negative, we'd go to the left. Whenever it's a not equal to problem, you have to just go in the direction of positivity or negativity. So this is positive, so we're going to go to the right. But remember, the special thing to do in a not equal to problem is to multiply by 2. So our p-val is going to equal the normal CDF. The left bound will be 0.949. The right bound will be 10, 0 and 1. And then we're going to multiply that result by 2. You have to double. It's a two-tailed test when you're not equal to, so we have to double here. Okay, that's going to give us a p-value of, and we'll go to the calculator for this. Times 2.343. So we've gone through our steps, we set our hypotheses, we found our significance level, we found our test statistic, we just found the p-value, and now we are ready to make our conclusion. Well, because 0.343 is not less than 0.05, the significance level, whenever your p-value is not less than alpha, okay, and this is even 0.01 for this problem. Whenever that's the case, we're going to fail to reject the null hypothesis. There is not sufficient evidence to show at the 0.01 significance level that, and now we need to know the alternative hypothesis in words. Be careful here, because the alternative hypothesis is not equal to. So the claim says the percentage of submitted online applications is equal to 0.5, but the alternative says not equal to. So this is a tough one to word. We're going to say that the percentage of applications submitted online is not equal to 50%. A little tricky in the wording there. We had to go to the context from the claim, but the alternative is a not equal to, so we're not going to say is equal to, we're going to say is not equal to. Okay, a little bit tricky, but that's kind of how all those not equal to's end up being. Okay, so there's a whole hypothesis test kind of laid out for you all in one place. Okay, there's homework for this lesson. You've got the homework from the previous lessons, and we'll be reviewing for the next 2 days to get ready for our next test. That's all for this lesson.